Mercury's orbital precession has been a subject of intense study over the centuries. Newton's equations, taking into account all the effects from the other planets and the Sun's rotation, predicts a precession of 5,557 arcseconds per century. However, the precession of Mercury's orbit is measured to be 5,600 arcseconds per century. This is a discrepancy of 43 arcseconds per century, or 1% from Newton's gravitation predictions. In relativity, this discrepancy is explained as due to the warping of space-time around the Sun. This explanation is not very intuitive and does nothing to help people understand what is really happening. In this video, we are going to illustrate how relativity's formula for mass-energy equivalence explains this difference. We are going to see how as Mercury goes around the Sun, its mass changes, and it is this change in mass that causes its orbit to precess. First, it is important to understand how celestial objects move in their orbits. We normally think, for example, that the Moon orbits Earth, but this is not quite accurate. Both Earth and the Moon orbit a point that is the common center of gravity for both. This point is called the barycenter, and it is located about 1,000 miles below Earth's surface. In this animation, we see the real motion of both Earth and the Moon around the barycenter. This point is always located in a line connecting the center of gravity of Earth and the Moon, and it helps understand the ocean tides. On the side of the Moon's gravity pulls in different directions than Earth's gravity. The weaker gravity allows the oceans to swell on the side of the Moon, giving us a high tide. On the other side of the Moon, Earth's rotation about the barycenter produces centrifugal forces that makes the oceans swell too, giving us a second high tide. The barycenter is calculated using this formula. The sum of L1 and L2 is the total distance between the two objects. This is how all objects orbit in space. It is also true for the Sun and Mercury. The difference in mass is a lot bigger than Earth and the Moon, but the effect is also there. Now let's see how Mercury's mass changes. We'll ignore the effects of the Sun for a moment. Let's assume that Mercury is a perfect sphere and density homogeneous. In this case, the geometric center and the center of gravity will be the same. Since gravity is the effect of space falling towards Mercury, as space moves through Mercury's mass, its mass has kinetic energy, there will be an increase in Mercury's mass given by the Lorentz factor. This increase will also be symmetrical all around, and the geometric center and gravity center will continue to be the same point. We now introduce the Sun in close proximity of Mercury. The blue line is the Sun's gravity decaying as a function of 1 over the distance squared. In this case, the Sun's gravitational field and Mercury's gravitational fields will add up. The side of Mercury's away from the Sun, the night side, will add Mercury's gravity and the Sun's gravity. This will result in a slight increase in velocity of falling space and an increase in kinetic energy and mass over Mercury's gravity alone. The other side of Mercury, the day side, will subtract the Sun's gravity from Mercury's gravity. The speed of space on this side will be lower, and the mass of this half of Mercury will also be slightly lower. The difference in mass between the night and day sides means that the center of gravity will move a little in the direction of the night side. Mercury's center of gravity will remain at the same distance from the Sun. It is the planet Mercury that will move closer to the Sun. The difference in mass between the night and day sides gets bigger as Mercury approaches the Sun, and smaller as Mercury moves away from the Sun. This means that Mercury's center of gravity moves back and forth closer and farther from the geometric center as Mercury moves in its orbit. The difference in velocity of falling space between day and night time also causes time dilation differences. This effect is also here on Earth. If atomic clocks here on Earth took these differences into account, they could be a few orders of magnitude more accurate than they are today. The change in space velocity between day and night sides causes Mercury's mass to change as it moves around the Sun. The Lorentz factor is not a linear function. Gains in mass due to increased velocity are greater than losses due to reduction in velocity. This also means that the location of the barycenter between the Sun and Mercury is also affected. The barycenter is deep inside the Sun. For illustration purposes, we'll show it as being outside the Sun. Now let's look at how this affects Mercury's orbit. The mass change in Mercury is a slow process as it goes around in its orbit. In this video, we'll assume that the change happens all at once for illustration purposes. Mercury's mass is at its highest when it is closest to the Sun. As Mercury moves away from the Sun, its mass decreases. When Mercury loses mass, the common barycenter with the Sun moves closer to the Sun. But the Sun has a given tangential velocity relative to the barycenter. When the barycenter is closer to the Sun's tangential velocity will make the barycenter line connecting both bodies to rotate faster. Let's look at what happens on Mercury's side. Mercury's momentum is defined as the product of its mass times the velocity. We can use standard Newtonian gravitation to determine Mercury's momentum as it goes around the Sun. The momentum decreases as it moves away from the Sun. When Mercury's mass decreases, its momentum remains as predicted by Newtonian gravity. This is only possible when Mercury's velocity increases, pulling Mercury faster on its orbit. This is how Mercury's loss of mass causes Mercury's orbit to precess. There is an opposite effect when Mercury is moving closer to the Sun, but the effect is not symmetrical. In one case, Mercury is moving in the same direction as gravity and, in the other case, against the direction of gravity. How did relativity get a good value for the extra-orbital precession of Mercury if it does not take into account Mercury's mass change? Well, this is not an accurate statement. In reality, relativity unwittingly introduced mass changes by assuming that time is variable. As it has been shown in this video on time dilations and mass increases are the same thing. When relativity assumes that time is variable, it implicitly includes variations in mass. This effect is also evident when we use relativity. We can see it in this animation courtesy of Colorado University. How a planet's velocity changes in an elliptical orbit. The velocity vector is shown in green. When Mercury's is closest to the Sun, it has the highest kinetic energy. When Mercury moves away from the Sun, its velocity decreases. The change in velocity implies a change in kinetic energy, and this results in a change in mass. There should be no doubt of the change of Mercury's inertial mass as it goes around the Sun. Once this mass change is taken into account, Newtonian gravity is all that is needed. While relativity only accounts for 1% of Mercury's orbital precession, when we have very massive objects, such as neutron stars or black holes, the effects of relativity will be much bigger.